Hello, my name is Rachel Buckles, and my presentation topic was on micromechanics and material selection for micromechanics. The article that I was assigned was Material Selection in Micromechanical Design and Application of the Ashby Approach, and listed here are the authors and the journal. The specific scope of study was micromechanics, so structures where the smallest feature is greater than 1 micrometer in length scale, but is measured in micrometers and is on a micrometer length scale. The main question was, how does the Ashby approach help optimize material selection in micromechanical devices? So for methodology, the model that I used was a cantilever beam. And listed here are the key equations for mass, inertial load, stiffness, deflection of the beam, and frequency bending vibrations of the beam. And so the material performance indices can be determined by sorting out which variables are material properties. And so for the first equation and the third equation in particular, the material indices are M1 equals rho and M1 equals Young's modulus. So the materials groups that I surveyed were metals and composites. And in the bottom right corner, you can see an illustration of the diagram that came from the article. So what are the best metals that can be used for a microstructure cantilever beam? Here the material indices are graphed, and that's M1 and M3, so that is Young's modulus versus density. So from this graph, you can determine that stainless steel or medium carbon steel would be the best choice for a micromechanical cantilever beam because they optimize Young's modulus while minimizing density. Similarly, in study 2, the best composites that can be used for a microstructure cantilever beam are, the best one is CFRP. So right here we have CFRP listed and GFRP listed on the graph. CFRP optimizes Young's modulus with reduced density much better than GFRP does. So CFRP would be the ideal choice. A summary of this paper is that the Ashby method can be broken into 3 stages: the concept, the embodiment, and the detail. The Ashby model can effectively model material selection for microstructures. Some but not all properties and functions from a large model, bulk model, directly translate into microstructure models. The outlying properties that do not directly translate have been identified and can be determined. And some of these outlying properties are Young's modulus, depending on the material, and intrinsic loss coefficient, which has to do with vibrations and acoustic loss. This paper demonstrates valuable examples of how the Ashby methodology can best be applied to determine the optimal materials of a microstructure. The paper does an excellent job of laying out the framework necessary for the methodology and makes helpful comparisons to show what principles translate from larger bulk structures to microstructures to best understand the concepts of material selection and design.